So I mentioned NP hardness before. Now that we've talked about reduction, we can revisit that definition and say problem X is NP hard if we can reduce some other NP hard problem to it. What that really means is we can use a solution to problem X to solve some NP hard problem. That means that solving X has to be at least as hard as the NP hard problem, making it therefore NP hard. Now, there's something sort of irritatingly circular or turtles all the way down-ish about this. So we want to show that some problem is NP hard. We've got some problem. We have to show that we can reduce some other NP hard problem to it. So we need that problem to be NP hard. How do we show that that problem's NP hard? Well, we can just show that there's some other NP hard problem that we could reduce to it, and so on, and so on, and so on. And it doesn't really seem like we could ever get anywhere this way. But the good news is that back in 1971, Stephen Cook gave essentially the original NP hard problem, and that is SAT. So SAT we know is NP hard, and the way that he showed that is really ingenious. He actually showed that if you had something that could solve SAT, you could use it to simulate in polynomial time essentially an NP computer, right? A computer that makes these non-deterministic choices. And since that's the case, anything that we could run on an NP computer, we can turn into a SAT problem, and therefore SAT is as hard as anything in NP. So that's great. So Cook got us off the ground here by giving an NP hard problem. So now we have something else to target. We have some other way, if we want to show that some problem is NP hard, we can just reduce SAT to it, and then we're done. But at this point now, there's actually a huge number of problems that are known to be NP hard. So if you encounter a new problem, it may already be known to be NP hard, or it may very well be that some known NP hard problem can be reduced to it, so you don't necessarily have to go all the way to SAT to do it.